Okay, so this is a general physics course, if you will. It's not really a course, it's more of a supplement to help you out with your example problems and all the problems that run from intermediate to difficulty in their level. And what we're going to be going over today is a projectile motion problem, and we're going to see how ratios change within projectile motion problems. But first thing is first, this is sort of my first video I'm putting out there on science in general. If you like the way I teach, please go to my website if you're interested in tutoring at tristancarmacy.com. And let's get on with the show here. So, when we're looking at projectile motion problems, we have a series of independent variables that we can deal with. And this is really how I want you to go about understanding physics and science in general, is that we have these things called independent variables, independent variables, and dependent variables. Okay, and then we'll get into exactly what independent variables are. And dependent variables are, a good example of independent variable is time, and a good example of dependent variables would be position, because we have some value of position everywhere we go, okay, in time. But with that aside, let's get into this projectile motion problem. So projectile motion looks something like this. That's projectile motion. We have a ball or something. We're throwing something at a certain angle. This is a certain angle. And and at a certain velocity, initial velocity in this direction. And it follows this path. And one of the reasons it follows this path is because we're on the Earth, and when we're on the Earth, we have this downward force due to gravity, okay? And the velocity downward, so we have a velocity upwards, that's the velocity where we are throwing it. The velocity downwards is gravity times time. So at every moment in time, gravity is going to be acting on this ball as it follows this path. And what we're interested in, or what I'm interested in today, is taking a look at if we have some y coordinate and some x coordinate. Here's x, here's y. Okay, and we're at some position here, A, for example. Okay, if we're at some position A, I'll call it a different variable. I'll call it gamma. If we're at some position here, gamma is at x equals 2. We are right here the ball is right here on this projectile, and it has some value. It has some value on the y-axis right here. We'll call that beta. Okay. So this is the x-coordinate, this is the y-coordinate, and both of these have names to them. And we're interested in is what if we throw this ball at this angle instead of the original angle at the same velocity. We want to know, in this example problem, we want to know what this value is. Okay, we can, and we'll get a formula for that. And let's start with getting that formula. So we know that we initially throw the ball like this, okay, and we have some angle to it. Here's the angle, okay, and then we have a vy, a velocity, the y velocity, and the y and the x, and then a total initial velocity. And we know that by the Pythagorean theorem, we could say that this squared plus this squared equals this squared, but I'm more interested in the trig. Okay, so we have cosine of theta. The cosine of this angle is equal to the Vx over V initial, and the sine of this angle is Vy over V initial. Okay? And we can rearrange these. We could say Vi is equal to cosine, or times cosine theta is equal to our coordinate, our velocity coordinate in the x position here. I'll redo that x. And Vi times our sine, the sine of this angle is the velocity in the y direction, okay? And so we can see that, so our velocity in this direction really only has this component to it, but our velocity in the y direction has this component to it as well, okay? Because this is acting in the y direction, in the negative y direction. So this is the positive part, okay? This is going up right here, and then we have some force due to gravity acting on our object due to gravity, like this. So we have to say that Vi sine theta minus gt is equal to Vy. All right, so now here's where the calculus comes into play. So what I want to do is I want to integrate these, okay? If I integrate this, so if I take the integral of Vx with respect to time, okay, I get position, I get x. Likewise, if I integrate the velocity in the y direction with respect to time, I get my y coordinate. And these here are the coordinates along our xy axis. Okay, and what do we get when we integrate this? So what we're going to get is we're going to have to integrate this. So we're just plugging this in for this. So Vi cosine theta equals, so that's our Vx part, and then we have to integrate that with respect to t. And if you don't know what an integral is basically a thing. It's an operator that takes velocity and it maps us to position. For right now, that's all you really have to know. Okay, and we want to integrate this between two time points, A and we'll say t. Okay, from t equals 0 to some t1, t equals 0 to t1 of Vy, which is V initial times the sine of theta minus gt. Okay, that is this part right here, dt. And what do we get from doing these? This here is Vi cosine of theta times t from 0 to t. And this here is, well, this is a constant. This is Vi sine of theta times t, because if we took the derivative of this, okay, we bring down the exponent. If you know how to take derivatives, we bring down the exponent, and we get this back. Okay, so taking the integral is like taking an antiderivative, minus gt squared, and I actually need a 1/2 there. I have a 1/2 gt squared. Okay, make that squared look better. Okay, and that is going from 0 to t. So then, if we were to plug t in here, this is just a t, right? This is t1. We need to preserve that t1 there. So our x coordinate at any given time is Vi cosine of theta times t1 minus vi cosine of theta times 0. So that's all we're doing. This here was a constant. We integrated it. That just put a t right here. Okay? And then what we did is we plug these values in. So the first one is this at t equals 1. And then the second term here is at t equals 0. Okay, if you don't know how to integrate yet, if you haven't taken calculus yet, this is still okay. This is a pretty easy problem to go through. And then our y is vi sine of theta t 1 minus 1/2 g t1 squared. Okay, and I'm just going to save us some space here. If we plug in 0 into here, we get 0, and if we plug 0 in for t, we get 0 here. Okay, and so what I'm going to do is, you can see that's happening right here too. 0 times anything is just going to be 0. Okay, so these are our two equations for our x and y coordinate axes. Okay, and so now we can say that we'll clean this up a little bit. We say that y, actually what I want to do here, so here we could solve for t1. t1 is equal to divide both sides by vi cosine theta. We get x over vi cosine of theta, and then we could plug it into here. So what do we get if we plug this t1 into this t1 into this t1? We get y equals vi sine, actually, you know what I'm going to do? I'm going to maybe skip just one step here. So if I put this, actually I won't skip a step here. Sine of theta times x over vi cosine of theta minus 1/2 g times x squared over vi squared cosine squared of theta. We just squared everything in here because it's telling us to square it in this equation. And so we can get that y is equal to, these will cancel, and we get a tangent of theta minus 1/2 g, and then we have this x squared vi squared cosine squared of theta. Okay, and we have this x right here too. I'll put the x right here. So this is an equation that tells us the y coordinate. If we come back up here, if we know what our x coordinate is, okay, if we know how far it's traveled, we could plug that in for x. If we know our initial velocity, we can plug that in. And if we know our angle, we can plug that in. And each one of these will give us, if we plug in values for each one of these, we get a y value. All right. I want to take this a step further. So when I was going through this, I decided that I want to take this a step further, and what we're going to do now is we're going to keep that equation in mind, okay, and I'm going to divide both sides by x. So if I divide both sides by x, I get y, I'll do it down here, so this x value, and when we have this x value, and this takes us, that will take us to x, like that. Okay, so I'm just basically dividing, I'm factoring out an x, and then I'm dividing by that x to get y over x. And this is a ratio now. Okay, this is a ratio. And this is an interesting concept, this ratio. So let's come up here and let's look at this projectile motion problem again. This ball, when we throw it, is following a path such that the x-coordinate, the x-coordinate and the y-coordinate preserve some sort of ratio. So if I have a y value here and I have an x value here, x divided by y, so say y equaled 2 and x equals 1, is 2. So y over x equals 2 in this case. We could calculate this if we knew the angle also. Okay, if we know the angle and the initial velocity and our x value, we can get this number as well with that equation that we just derived, with this down here. And so what I'm going to do is I am going to say that y over x equals some constant s. Okay. And so s is equal to the tangent of theta. This is just that same equation I wrote below. I'm just repeating it up here. 2g x v initial squared times the cosine squared of the angle. Okay, that's our original equation. And now let's see what would happen if we took the derivative of s. So this is going to be a little bit more advanced. What if we want to know how this ratio changes as we change our theta value? So take this to be instant 1. So this is scenario 1. Okay, and then scenario 2 would be maybe something like this. So our angle is a lot less. Okay, we could still get an x and a y coordinate out of this, but we want to know how this constant changes. Okay, as we change this angle, so we could take the derivative of s with respect to theta. Okay, now this is going to require some calculus. So if you haven't had calculus yet, then it might be a little bit tricky to follow. But what we get is that the derivative of the tangent of theta is secant squared of theta. Okay, and then if we take the derivative of this, we have 1/2 g x over v naught squared. This is all a constant. And then all we have that has theta in it is this 1 over cosine squared theta. Now I'm going to make a leap here. And this leap is going to be assuming that you know how to take the derivative of this. Okay. So we need to take the derivative of this. So more accurately, I need to write it like this. So d theta of this. And what that ends up being is secant theta tangent theta. Okay. I'll leave that as a practice problem for you. So we get d theta s is equal to secant squared theta. We just have the same thing up here. Secant squared of theta minus, we have this here, this is actually 2. There's actually a 2 right here. So we get that 2 over 2. I'm skipping a lot of steps here. I hope you're following. We have g x v naught squared secant theta tangent theta. And then we can clean this up a little bit. You can factor secant out. Secant theta minus gx v naught squared tangent theta. And here we have described now how, here's situation 1 in our projectile motion, and then situation 2 could be something like this, where we have some angle 1, or some, this is, I said that was situation 2, so I'll call that angle 2, and here was angle 1. Okay. And what we found was an expression for how this constant, how the constant between the x-coordinate and the y-coordinate changes as we change our theta value. Okay, so I hope this made sense. Some of this does require calculus, but I hope that this exposes you to calculus in a way that we've applied it to an example problem. And this might be daunting, right? This might be daunting. If you haven't taken calculus yet, then you can really only understand some of this. And I'll be going over, this was more of a difficult problem. And I'll be going over other problems that are not as difficult as this, but I think this is a good example of showing how we get stuff like this in our kinematic equations. This 1/2 gt squared, we see that in our equations for projectile motion, right? And then you've probably seen stuff where we have the vi, this. You've probably seen stuff like this, right? What's new? What was new? Something that you probably haven't seen in your courses is this right here, and then right here I decided to really be creative and to employ some calculus to see how these ratios change as we change our angles. Okay, and you could see here we have this constant. These are the things we would control at some x value and at some value for our initial velocity, we can get an equation showing how this changes. And so I will see you in the next one. Stay tuned.